Yeah, should I start?
I will introduce you.
Okay.
Okay, so it's 1 minute behind the time, but I think given that it's the first seminar here in the half, it's a tremendous success. Okay, so today we have Ethan Lay. Let me tell a quick story about Ethan.
Uh-oh.
So I usually take this opportunity to suggest every graduate student, whenever you have a chance, to go to Boulder Summer School. So that's where I met Ethan. It was in 2016. I talked to him a few times. I saw that he had like 5-6 papers published. He mentioned he's applying next year. And I thought, wow, he's going to get a good postdoc. And a few days later, somebody asked me, oh, did you meet the undergrad? No. Oh, a few days later after that, turned out that he's applying for graduate schools and is studying his 4th year of college, which still is blowing my mind. Now he's a PhD student at MIT. He's working, I think, with Senthil, and it's a real pleasure to have you here.
Yeah, thanks. Yeah, it was all downhill after Boulder Summer School, man. Yeah. Thanks for inviting me. It feels awesome to come and give a talk. I feel, yeah, it's just super cool to get out. I've never been to ground before, so yeah, pretty great. So I'm going to be talking about some stuff on TTG, which is twisted trilayer graphene, which is some experimental, interesting system that has been getting a lot of attention recently. The whole kind of moire materials and strongly correlated physics in graphene systems and stuff was kind of started at MIT, where I go to school, but I don't know, I guess it somehow seemed like too mainstream for me to like do research in for a while. And but then, okay, I realized that actually that was just me having a bad attitude. There's actually like lots of really cool stuff going on in this field. And in particular, in March, I guess, of this year, we heard from Pablo at MIT that they had some interesting results on this system that I'm going to be telling you about today. And our minds were totally blown when we saw what data they had. So I'm just going to talk about kind of their experiments, what they did this year, and maybe talk about some stuff that we think we might understand about the system. I don't really know exactly what people here, what the audience is. So if this seems like I'm being too technical or too boring or whatever, just ask questions, and I may not be able to answer them, but we can at least talk about them. Okay, so I have a few, I guess 2 slides telling people or reminding people what has been going on in twisted bilayer graphene. So I assume everyone has kind of heard of this. Basically, in 2018 now, people discovered that if you take 2 sheets of graphene and you place them on top of each other, but you kind of twist them by some small angle, which turns out to be about 1.1 degrees, a bunch of interesting things happen. So, okay, so this is kind of, you have graphene, which is some hexagonal lattice. You have another graphene, and you twist them, and you get something that looks like this figure up here. Okay. Now, what happens in the system if you kind of people many years ago, Alan McDonald and Castro, whatever his name. Sorry, I never remember I've never said that name out loud before. Anyway, people had predicted, based on some simple model of how electrons hop around in this system, that what would happen when you created this kind of twisted stacked structure, what would happen if you just trusted these, you kind of did some tight binding calculation in a system like this, is you would find that the energy bands that are formed by the electrons in this system kind of do something pretty interesting. Namely, you get some energy bands, which are right kind of by the Fermi level, which are very, very flat, meaning that they don't have a lot of kinetic energy. The electrons in these bands don't have a lot of kinetic energy. And these kind of flat bands are separated in energy by kind of a large amount from all other stuff that's in the system. So I should have included a picture of the band structure here, but basically you have like a whole bunch of stuff going on at very far away from the Fermi level, which is kind of very complicated, and right in the kind of range of energies that people are studying in experiment, you have a few very, very flat electronic bands. And in particular, what happens in the system is the bandwidth of these flat bands is some number, which is a lot smaller than the kind of like energy scale of the interactions between these electrons in these flat bands. And that scale is much smaller than the distance to other energy bands. So basically, the system is you have a few very flat bands, and the electrons in these bands are interacting with each other very strongly, and they kind of exist in their own isolated universe, and other aspects of the problem aren't important. So this is interesting for like condensed matter people because it's a nice way to engineer a system where you just have electrons and they're interacting very strongly with each other and they do something interesting. Okay, so in particular, so this third bullet point is kind of telling you what the degrees of freedom in these flat bands are. So you have electrons and they're in graphene. So you might remember that graphene, we have these two different sublattices. So there's a degree of freedom from that. The electrons have spin, and the graphene, you have like these K and K prime values in graphene. And so there's a degree of freedom in that. So you have these 8, it turns out the counting works out to be 8 different types of electrons in these flat bands. And what they do is pretty cool. So why do people care about this, right? So what was found is that these kind of systems, this system displays a lot of interesting things. So one interesting thing that happens is that you get insulators in places where you wouldn't think there would be insulators. So you take these bands and you kind of put the chemical potential so that the electrons kind of fill up a little bit of the band, but not all of the band. And because they're interacting very strongly, they kind of like, they form some kind of insulating state where the electrons are trapped and don't like move around, but we don't really know what exactly is causing them to form this state and what exactly they do. And then another thing that was interesting is that they also found that the system becomes a superconductor, and it becomes a superconductor kind of like where the filling of the electrons is right next to the filling that gives you this insulating regime. So let me laser point here. So this is this figure is telling me what happens. This is telling me the conductance of the system as I change like the number of electrons that are in these flat bands. And you'll see that what happens here is that you have like very small conductance at these 2 points. That's where you kind of like completely fill up the flat bands with electrons or completely empty them with electrons. But there are also these places here, which is kind of like you have only partial filling of the flat bands. And here the conductance goes to 0, which is kind of like a little bit, doesn't make sense within a free electron picture. It has to require some kind of interactions. And if you look at you do a more detailed thing and you measure the temperature as a function of density, you find this region where you have a superconductor. That superconductor turns out to be like right over here.
You mean resistance is a function of temperature and density?
Yeah. What did I say?
Temperature is a function of density.
No, that's not, yeah. Resistance is a function of temperature and density. And you find that there's a superconducting region, but the superconducting region like lives right next to this this place where it's actually an insulator where the electrons are trapped and aren't conducting. So understanding what's going on has occupied a lot of people's time.
So this negative 1.6 would correspond to this
yeah,
peaks in conductance. So I assume this is like a 4 Kelvin measurement.
This measurement?
Yeah.
Yeah, that sounds about right. Yeah. Yeah.
So if you go to 1 Kelvin, this you would have this two region would go, the conductance would be infinity, right?
Different sample. Different sample. This is a 3-terminal measurement. It's a 4-terminal measurement. And it's different sample.
Yeah, maybe this is not the best. Well, this kind of region here of where the resistance is high is what I'm talking about. I'm referring to this thing.
This sample should have same physics, right?
So the reason that the non-insulator get replaced by a superconductor at low temperature is due to sample inhomogeneity.
Yeah.
You just need one superconducting channel to connect the source and drain to measure a superconductor. Right? Even though probably a majority of the sample is a non-insulator.
Yeah. 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 This doping regime is an insulator. It's this thing. But yeah, you're right. Different pictures. Anyway, so the question that two of the questions that like you could think to study here are what's going on with this region where you have this insulator, where you're adding a fractional number of electrons into these bands and they're insulating. So what's happening to the electrons? What kind of like symmetry breaking kind of thing are they doing to give you an insulating state? And then perhaps related is what's up with the superconductor. So you want to know, you have a superconductor. Okay, what's the pairing symmetry? What is the like glue that's binding the electrons together in the superconductor? Is it related to this insulating thing, that insulating region that appears next to it, and these kinds of questions? Okay. So this has kind of occupied the attention of.
Can you remind us the mean-free path of the sample in this kind of a typical samples?
Mean-free path, it's pretty big. I mean, these are pretty clean. You can get there, yeah.
So then how do you know this is not just phase coherent single electron transporter rather than superconductivity?
They look at like Fraunhofer patterns and stuff, and I mean, you're right. You can't do the Meissner effect or anything like this, so you have to be careful and do phase sensitive measurements like that. But those exist, not on my slides, but yeah. Yeah, I mean, this is an important point, right? Because there are other systems where you would look at a picture like this, and it turns out actually not to be a superconductor.
Have they done the flux condensation to show it's H over 2E rather than 1E?
I don't think so.
Then you don't really know this is superconductivity.
And now you're going to do superconductivity.
Well, you can have autonomy. It's just that the question is autonomy of pairs or not, right? So the only way you can prove is 2E is do a flux condensation. You can see that the periodicity is H over 2E.
I think they have something like that. It's in the Fraunhofer pattern. When you tunnel junction, and then you know the size of the tunnel junction.
I think you're right.
That's not
this is an experimental problem that we can talk about.
Yeah, maybe I think the very first paper on this actually has some comments about like looking at the analyzing the Fraunhofer pattern and the critical current. And I don't know, maybe I don't know if that will be satisfactory, but you should check that out.
You can take a gold ring, make it small enough and cool it down. You will see something looks like superconductivity, but it's not. It's just the mean-free path is bigger than the green. And you do a flux condensation, you will find it's H over E, not a 2.
Will you have like a sharp?
Yes.
They also found like a sharp current turning on as a function. Like their critical current has the sharp step, for example.
What do you mean sharp step?
Like you look at you look at yeah.
That can be you can have a thermal runaway of the sample, right? Should have the sample. It's not decisive. It has to be flux condensation.
Well, then maybe you can choose to ignore or not ignore everything I'll say about superconductors based on the information you have at the present moment. So anyway, so these are the kind of questions we're going to ask, and be interested in like what's going on with the superconductor, quote superconductor, what's going on with the insulating regime, what kind of like flavor, degrees of freedom are involved, etc. Okay, so last two slides have been about this bilayer system that has attracted most of the attention so far. But basically this year and last year, people started looking at a new system, which actually doesn't really differ too much from what I was just talking about, namely twisted trilayer graphene. So you take basically these two sheets are graphene and are twisted at some angle relative to each other. This is just like the bilayer case I was describing in the last slides. And you just take another layer of graphene aligned with the first one and you stack it on top. Okay, so you're just doing this. And okay, what happens when you do this? Well, you can try to do the same kinds of like single particle physics that people did when they were thinking about the bilayer case. And if you compute the band structure for this model, you find something that looks like this. So this is a dispersion, and there's the momentum axis got cut off. But basically, what you find is you find some bands that have a very small bandwidth, which are these orange guys, and then you find an extra band which is kind of has this Dirac point placed in the brilliant zone. And essentially, you can actually prove that if you just look at the single particle physics, this problem is exactly equivalent to a twisted bilayer graphene problem plus a extra Dirac cone that comes into the dispersion like this. Okay, so this is what the single particle physics tells you, and in fact, there's lots of stuff going on over here, but people have done experiments to kind of check that this kind of decomposition of the degrees of freedom is playing out in the real world. Okay, so it's basically just like this bilayer graphene plus this extra Dirac fermion. Okay, so one other thing I should say here, well, I said it on the slides, but is that there's a mirror symmetry of this setup here. So I'm twisting this at some angle and I put it here, and then this guy is aligned with this bottom layer. Okay, so there's a mirror symmetry about like reflecting these guys through the sandwich. Okay.
So is this you start from a tight binding picture
to derive that? Yeah.
Okay, so then what's the effect of another layer? It just provides another periodic potential, right?
Yeah, basically, yeah.
And then that's treated as a tight binding as well. Electrons allowed to hop between the layers.
Yeah. It's just like what I was doing before. It's like just there's one more thing you can hop to.
So is there a easy way to understand? Because now you have a very flat band.
Yeah.
You have a direct like band.
Yeah.
Is there an easy way to understand which electron is
on the Dirac band?
Right.
Yeah. So thank you. So indeed, this is where this mirror symmetry is important. So these two bands have different colors, and basically it's indicating that the electrons that are kind of flat, that have a very small dispersion, are the ones that are mirror symmetric. So I take my electron operators on these three layers and I can decompose them into, I have it on the next slide, I believe. So I can take my electron operators on the three layers, 1, 2, 3, and I can form like symmetric, a combination which is invariant under this mirror symmetry, and then a combination which it transforms to minus itself under the mirror, the symmetric and anti-symmetric combinations of this mirror thing. And when you write the free Hamiltonian in this basis, it becomes this, where D is this derivative thing, right? So basically, this is the Dirac cone I was talking about. This is the mirror odd sector. It just forms a Dirac cone, and it doesn't do anything else. Decouples from the system. And then the other degrees of freedom form this matrix. What this is not important. This is the bilayer graphene single particle problem. So the problem decouples into bilayer graphene plus this extra Dirac cone. And in the absence of anything that breaks this mirror symmetry, you're just adding this extra decoupled Dirac cone, and it doesn't really do anything. Okay. So the reason why I'm talking about this is you can actually consider what happens when like this extra Dirac cone like enters the picture and starts interacting and hybridizing with the other bands, and you do that by breaking the mirror symmetry of the problem. So as experimentalists, there are two things that are relatively easy to do. One is you can establish some electric field that points from one layer up to the top layer, right? So I'm going to put some gates here, and then I'm going to put them at some potential, and I'm going to create some potential that goes throughout the layer like this. And the other thing you can do is you can put a magnetic plane in, a magnetic field in plane of the sample. Okay. So this breaks the mirror symmetry because I put the magnetic field has this handedness, right? And when I do the mirror, it flips, right? So when you add these external fields to the system, they appear in this Hamiltonian, like this form. Doesn't really matter. The point is that it couples the mirror, the kind of twisted bilayer copy to the extra direct fermion, and they kind of get coupled together and do stuff. Okay. So the point is by tuning these external fields, the magnetic field and this potential like that, you can kind of mix the Dirac fermion into the other degrees of freedom and look at what happens. Okay. Okay, so that's basically the setup of all we're going to do in the remainder of the talk is try to understand the experiments that people do in the parameter space of this magnetic field and this electric field. Okay, so we'll just look at the data and then try to see if we can understand that data. Okay. So here's so I'm going to talk about some experiments that were done earlier this year. There was one set of experiments done. Well, I'm mostly going to be focusing on some experiments done from Pablo's lab at MIT, and Philip Kim's group at Harvard also had some stuff that we were looking at. Anyway, so this is the kind of stuff that got me interested in this problem. So here what they're doing is they're studying the I should have said by the way, this trilayer graphene system also is a superconductor and also has these kind of like symmetry breaking insulating things, because as I was saying, it's kind of just a decoupled direct cone plus this bilayer graphene thing, right? So just like the bilayer graphene problem, it also has this superconducting thing. But the superconducting phase in this trilayer graphene system is more interesting. One interesting aspect of it is this. So let me just decode this here. So here they're again plotting the resistance as a function of this is filling of those flat bands, and then D is the electric field that they're applying out of the plane, and then this vertical axis is magnetic field. And you can see that this blue region, okay, if we just judge superconductivity by resistance, you can see that this region survives up to at least maybe 10 Tesla. There's some superconducting stuff up here, zero resistance stuff up here at large fields. Okay, that's just a number, but it turns out that 10 Tesla is actually very big in this system. By big, I mean if you normally, superconductors don't like magnetic fields, right? Why don't they like magnetic fields? Well, one reason, there are several reasons, but one reason is that normally you're pairing singlets when you form superconductors. The Cooper pairs are made out of singlets, right? And if you try to apply a very strong magnetic field, you're going to break the electrons don't want to be in a singlet. They want to break and point along the magnetic field direction, right? So what you have to do is you have to, in BCS theory, you could say, okay, well, if I break a Cooper pair, then I get some energy because I can align the spins with the field, but then I lose some energy because I'm breaking the pair and there's some condensation energy associated with that, right? Okay, so what you have to do is you have to ask, well, how big of a magnetic field do I have until I start like breaking? It becomes favorable for me to break these fields, these Cooper pairs, right? So you get some number which is usually called to like the Pauli limiting field. Okay, this BP thing. And if you make an estimate for what this is using BCS theory, it turns out that it has some relation to the critical temperature if you do these calculations in BCS theory. Anyway, the important part here is that when you calculate what this BP is supposed to be in the system, it's pretty small. It's about maybe a factor of 3 smaller than what the actual critical field is. Okay, so you have to be a bit careful about how you interpret this kind of calculation comparison here, but it seems to be saying that if you have the superconductor that we're seeing in experiment is probably not a spin singlet superconductor. If it was a singlet, you would have this pair breaking effect. Okay, so you know, there are details there, but for now, let's just take that on at face value. The other interesting thing, which is cool about these experiments, is this plot, which is pretty cool. So this plot is again where we have resistance, right? This axis is temperature. Okay, the T got cut off here, but this is temperature and this is field. And so, okay, we know it. You know, we saw on the last slide that the large enough fields do kill the superconductor, but it turns out they kill the superconductor in this really weird way. So, right, so we increase the field, and the superconductor where where we have zero resistance goes down and goes down and goes down and is killed at say 8 Tesla here. But then I increase the field more, and the superconductor comes back in higher fields. Okay, so that's pretty strange, right? That's pretty strange because superconductors are not supposed to like magnetic fields. Like there are some, you can think up some kind of exceptions to this, but the exceptions are all weird and exotic and interesting and blah blah blah. Okay, so we have this, which needs to be explained. And the other thing which is interesting about this plot is that here, okay, you see the critical temperature of a superconductor. You know, there's a revival up here. The superconductor comes back. But if you kind of plot, it's a bit hard to see on color plots like this, but if you kind of measure where the resistance reaches some like half of its normal value, where the superconductor is like beginning to form, that is actually kind of a smooth function of magnetic field. So it might be about like this contour on the plot or something, right? Why this is an important distinction to make is that, you know, if I plot this kind of curve where the resistance kind of dropped to be small but is not zero, that's kind of telling me like where pairs are starting to form, where Cooper pairs are starting to form, right? And then this line here is telling me where I have like phase coherence and where the Cooper pairs are actually like, I have this like macroscopic rigidity to the wave function and all this other stuff, right? And zero resistance. Okay. Now normally we would you know, if you're trying to the process by which these pairs like come together and start to form the Cooper pairs, this like process should also kind of be related to the, you know, this critical temperature. But here they kind of follow different dependencies on the field. So this is kind of a weird feature of this data that needs to be explained. Okay. Okay, so everyone good with this? This is kind of the setup for, this is like the input for this project that I was working on. Okay.
Well, I was actually wondering, is there any like hysteresis relationship? Like, does it matter which direction the field come from, or is it kind of...
Oh, for this thing?
Yeah.
Yeah. So the existence of these two pockets of superconductivity, at least in this experiment, I mean, they always existed, but this transition is a first order transition. So like the way in which you go from this to this, there is hysteresis in that, in the precise like value of this magnetic field. So this is probably some first order transition. But at least on the device that was looked at in this paper, they swept it back and forth a few times.
How good is the alignment between the field and the...
Yeah, so I don't understand how they do this, but I think it's very, I guess you probably understand how this is done, but it's very good.
They have an accident. So which means that, but just to 30 millitesla out of time probably is enough to significantly suppress this.
Yeah. No, the critical field of this superconductor is like 10 millitesla or something, very small. And notice that the in-plane field here is already 10 Tesla. So they have sensitivity to, you know, a part in 10,000 or something to get the field in plane. So they can really measure that precisely by looking at how the superconductor is killed. Yeah.
Because a small misalignment would put some vortices in the system, right?
Mm-hmm.
So then you will be dominated by that small component.
Yeah. Yeah, so they have to be very careful about aligning it exactly in plane. Yeah. I don't know. I mean, it seems hard to me, but maybe I don't know. Maybe it's maybe.
So what you could do is that you can go to the Tesla where it's suppressed, and then can start to apply a small out of plane magnetic field to make sure that superconductivity doesn't reappear, right? Because if it's some kind of flux effect, then it will reappear. I don't know if that's exactly what they did, but I know they have a vector magnet. This is a kind of a tuning they do to make sure it's not flux.
You know, if I take a piece of lead, I polish one surface, I apply a field parallel to that surface. And the upper critical field where the superconductivity appears is higher than if it's perpendicular. I'm just wondering whether the same physics is here or not.
I don't know.
It's a 3D system. It has almost no spillover coupling.
Yeah.
And, yeah, it's apart from spin triplet pairing, it's hard to.
The simple explanation there is basically because you have a surface there. If you think about the upper critical field, it's flux quantum divided by pi the coherence length square.
Yeah.
Right? So if you have a dimension that's smaller than the coherence length, then your upper critical field will be bigger. So here you effectively have when you line up the field parallel to the layer, now your coherence length is the thickness of the layer. So if you take the flux quantum divided by pi to the thickness square, what is that value?
But there's no orbital effect.
No. Just for the sake of the number. You trilayer, right? You have a thickness. And then you take the flux quantum divided by pi times that square. What is that? That should be a scale, right?
Yeah. So, well, so let's see. The number I remember is that you need like the number of the flux through a Moret's unit cell.
Flux quantum is 2.07 times 10 to the minus 7 Gauss centimeter square, right?
Yeah, I think you need like 100. You need like 100 Tesla to get flux of pi through a Moret unit cell, and a Moret unit cell.
So
I don't know however big that is.
1 nanometer.
Yeah.
I don't think that.
No, just compared to the field scale.
So 1 flux per 15 nanometer square is 15 Tesla. And the Senthil here is 1 micron wide and 1 nanometer thick. Is it the point here that the demon is bigger than
Yeah. That's okay. The point is it's just bigger than no matter where you put it. I mean, so the point of this slide was just, I mean, it doesn't really matter if it's perfectly aligned or whatever. You're still breaking you would still conclude that you should have already broken the pairs if they were singlets. This is just a Zeeman effect, right? It doesn't really depend about the alignment. Maybe you can argue that some of this kind of phenomenology is more sensitive to being good about the alignment, but at least the fact that it's not a sequence superconductor needs to be explained. Okay. So our strategy here, is our strategy here. So Chinese history people will know this phrase, right? We're going to we're not going to try to like go make big jumps about how we address this problem, right? We're going to try to remain on firm footing. So in these kind of problems, doing microscopic theory is very hard. And even if you can do it, you don't really know if you're doing anything correctly at this stage. Well, I mean, that's being not quite true, but it's very hard for someone like me, especially, to do something that I'm convinced is right if I try to take a microscopic approach. Okay, so all we're going to do is we're going to look at the data that I just presented, and okay, we're going to do this stuff on the right. We're going to try to just do some phenomenology and see if that gives us anything. Okay, So okay, here's the first kind of observation that goes into how we organize our thinking is the following. So this is a Landau fan diagram. So this is perpendicular magnetic field. Now they're going to study again. They're going to do transport studies in a perpendicular magnetic field as a function of how many electrons they put in these flat bands. And you see that, okay, so this -2 here is where this insulating state that I was talking about is forming, okay? And it has, okay, it has some slope here as a function of the magnetic field. These slopes basically tell you like what's the degeneracy of the electrons that are living in these states.
So the x-axis is some voltage, the gating voltage.
Yeah, filling for the number of electrons that you're putting into the system. Okay, and it's a bit complicated, but essentially what's going on here is let's look at zero filling, which is okay. We have half filling. You can see that there are a bunch of states that are coming out of this filling that have. You can look at the slope, and that tells you what the degeneracy of these states are. Okay, and it's a bit tricky, but you know, there's a 2 here, and then there's a 6 and a 10. It's kind of hard to see by eye, right? But you compute these slopes, and you get something like 2, 4, 6, 10. Okay, the important part being that these are separated by 4. Okay, whereas if you come look over here, there you get 2, 4, 6, 8, 10, and these are separated by 2. So what this means is that the degeneracy of your electrons changes between this point and this point. So when I'm filling up electrons, I have less degeneracy over here than I have over here. Okay, so the degeneracy that I'm talking about, I mentioned this a while ago, but you know, in this problem we have our spin degrees of freedom, the electron spin, which is degenerate in the absence of any other perturbations. And we have the valley of the graphene, right? So we have the spin and valley, right? And that gives you this 4 here. But here we only have 2. And so what needs to happen in order to get a 2 is we need to have some kind of breaking of this degeneracy of the electron flavors, okay? And the problem is then to figure out what kinds of, how the degeneracy gets broken, right? So you can imagine one way to break that degeneracy is to just get rid of all the up spins and only have down spins, for example. Or you could get rid of all the like graphene K prime valley and only keep the graphene K value, right? And figuring out the right way to actually do this and the right way to actually select out the degrees of freedom that are, degenerate here is kind of complicated. We have some input from that was developed by basically some people at Harvard and Berkeley and other places that allows us to kind of make some statements about in a strongly interacting limit. So we're essentially going to take motivation from that, and maybe this is like the most technical slide here, but basically, okay, this is what I was just saying. We have our graphene valley and we have our spin. Those are the degrees of freedom, right? So we need to polarize some flavor to reduce this degeneracy near -2, near where this -2 filling is, right? And so we know that, let me just go back to this slide. So this is where, why am I focusing on this point? I'm focusing on this point because the superconductor occurs over here in this region, okay? So the degrees of freedom which go into making the superconductor are the same as the degrees of freedom which are coming out of this state, right? So the superconductor is being built on this like less degenerate state, okay? So the electron, once we figure out what the right degrees of freedom are here going into this Landau fan, we'll know what degrees of freedom go into making this superconductor, okay? So now, given this, okay, now we know that, well, our theoretical prior is that when we have superconducting, when Cooper pairs form, they like to form between electrons that are related by time reversal symmetry, okay? In particular, we have this degree of freedom, this graphene valley degree of freedom, right? So you remember that the valley is just, when you look at the graphene problem, when you look at the graphene dispersion in K space, you have these Dirac cones, right, at the K and K prime values. So the K and K prime labels here are really like momentum labels in the Brillouin zone of graphene. And in particular, they're, they're momentum, and so they're acted on by they're not preserved under time reversal. So the time reversal partner of K is K prime. Okay, if you remember the graphene, you have K and K prime. They're at opposite places in the billion zone. So we want to build a superconductor. So I have an electron that wants to form a Cooper pair and another electron. Well, if the two electrons going into this pair are related by time reversal symmetry, then one electron should live at value K and the other should live at K prime, because they're at, K is equal to minus K prime in the billion zone. Okay. So what this means is that I shouldn't like, for example, I shouldn't just put all my electrons into value K. Because if I did that, then there would be no electrons around to form the Cooper pairs. Okay. So we're not going to do that. So then the other degree of freedom we have is spin, right? So okay, what should we do with the spin? Okay, what we're going to do is for now we're just going to be general and say the spin in each valley is just going to point in some direction. Okay, so we're not going to have like both up spins and down spins in valley K. We're just going to have one spin, and in valley K prime we'll also just have one spin. Okay. Now these spins can point in some direction, which for now is going to be arbitrary. Okay. Now the way in which we decide in which ways the spins should point in each valley is, well, the way it's really decided in reality is there's some term in the complicated model for this Hamiltonian which couples the spins at valley K with the spins at valley K prime. There's some term like this if you were able to actually like compute the full interacting Hamiltonian and in the subspace blah blah blah, you would get some term like this. And so there's some term like this, right? Now if this coupling is bigger than 0, then the spins in each valley will anti-ferromagnetically align, because that's right. And while if J is smaller than 0, they will ferromagnetically align. Okay, so unfortunately, we don't really know what the value of JH should be. We don't know the sign of JH, really. It could be positive, it could be negative, okay? But it turns out there's a way to settle this, which is pretty interesting. So I think you can ignore the top part. We're just going to basically do Landau. We're going to do a phenomenological analysis of the superconductor using the fact that the superconductor has like electrons in K valley with spin in this direction and electrons in K prime valley with spin in another direction. We're going to use that and then just put it into a Landau-Ginzburg theory and kind of see if any phenomenological things appear in this analysis. Okay. So let's first consider what happens if I take this JH to be smaller than 0, so that I want the spins in the valleys to be ferromagnetically aligned. It turns out what happens in this case, maybe we can talk about this later if anyone happens to be interested, but it turns out that if you compute like the order parameter manifold for the superconducting order parameter in this case, it turns out to be SO3. So like, in a normal superconductor without any other degrees of freedom, the order parameter manifold for the superconductor would just be a circle, right? I have my order parameter, it's a phase, it can take any value in a circle, right? But here we have these spin degrees of freedom also, right? And they're also being ordered, right? Because they're being locked in these two values, right? So the direction in which the order parameter can live is actually, it doesn't live on a circle, it lives in this more complicated space, okay? Now, what's interesting about this particular space, SO3, is that it doesn't have any, its fundamental group is trivial. Why this is important is because, remember, this is a two-dimensional system. So when I talk about the superconducting transition, it's actually this BKT transition, if people have heard about this, right? It's basically what's happening is the superconductor is being killed by vortices entering the superconductor and proliferating. Vortices only make sense if you have something to, like the vortex in a superconductor is the phase winding around the circle, right? So if the order parameter doesn't live on a circle, it lives on this SO3 thing, then a vortex is going to be like the order parameter winding around in this manifold, but that there's actually no way to wind around SO3. Anyway, the consequence of this is that there actually don't exist any vortices in this kind of superconductor. And a consequence of this is that the critical temperature would be 0 for this case. You actually can't have a superconductor in 2 dimensions with this kind of structure. Okay. Anyway, so that, okay, this is details, right? On the other hand, if you make this other assumption where JH is bigger than 0, you can do some math and you calculate that the order parameter manifold there are some vortices and the critical temperature is finite. Okay. This slide is just supposed to, say that we don't know what this is, kind of like giving you a flavor of how we're approaching this problem, right? We're not trying to, we can't assume anything microscopically because the problem is too hard to deal with microscopically. But if there are some general statements that you can just say, well, should it be antiferromagnetic or ferromagnetically aligned? Well, I know I can look at the critical temperature and make some statements about that. Okay. So there's some phenomenological constraints that can come in here. So yeah, so this is like a summary slide so far. So basically what we're proposing here is that the superconductor is not really it's not really a spin singlet or a spin triplet. Okay. The electron, the degrees of freedom in the Cooper pairs are not spin singlet or spin triplet. They're actually a combination of the two. This is allowed because the spin symmetry itself is being spontaneously broken by the interactions that polarize the subspace that I was talking about. Okay. So basically what happens is here's my in-plane magnetic field. These are the directions that the spins point in these two values. They're pointing in this direction for the reasons that I talked about in the opposite slide where JH has to be greater than 0. So they're doing this. And then when I turn on the magnetic field, they just kind of the electron in valley K and the electron in valley K prime, they just go like whoop and they align with the magnetic field smoothly. But there's no like poly breaking because the electrons are never bound in a singlet anyway. They're just polarized in these directions in these values. Okay. So just the most natural like conclusions from this strong coupling analysis that I didn't really talk about, but the most natural conclusions are that give you a natural way to expect that there should be none of this poly limit, this singlet breaking process should not be relevant in the present problem.
How about the spatial symmetry of the wave function?
Oh, the like P wave, S wave, whatever. Yeah. So the good or bad part of this is that we have this extra degree of freedom in the valley, right? So we need the wave function for the electrons as a whole to be antisymmetric, but in the valley we can choose the valley to be symmetric or antisymmetric. So we don't really have any good theoretical prior as to whether the pair should be like valley singlet or valley triplet. But if you knew which one of those it was, you would know, for example, the parity of the wave function. So far, what we're saying has nothing to do with no constraints on the actual orbital component. Yeah.
So if I take let's say not your trilayer, let's say I just deposit bismuth on a cold substrate. Also putting the atomic layer thick. And then I apply field parallel to the surface. Do I get the same physics?
So you're putting it at a low temperature enough so that's a superconductor?
Yes.
No, then you'll be killed if you put a big enough field. Then the pairing is singlet, and then you'll be killed when you get to the poly limit for that material.
So this has
the important part here is that we have the important part about these kind of systems is they have like the electrons have more degrees of freedom than they do in a normal metal. So there's also this valley degree of freedom, right? So they can, this whole stuff about their flavors polarizing and the interactions, blah, 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 is kind of associated to the fact that they have these more degrees of freedom.
The valley here is the unit cell valley.
The valley here is the graphene valley. Yeah.
So basically the superconductor is defined on the Moore supercell, but it still has information about its momentum on the unit cell. And that's what's giving it. Yeah. You should think that the actual graphene scale for the lattice constant of graphene is like super small. So it's just like some internal degree of freedom that is just so that's what I mean by K. The K sub M will not appear in any of these slides, I think. Yeah.
Just to clarify, when you talk about, you briefly mentioned valley singlet or valley triplet. By valley triplet, do you mean same valley pairing or the fact that K and K prime have the same sign their wave function.
Yeah, symmetric. So like you know, the thing that gets an expectation value will be like C electron operator, some matrix electron operator, and that matrix can either be like valley X or it could be valley Y. So depending on if it's valley X, then you want your spatial wave function to be anti-symmetric. If it's valley Y, the other way around. Okay. But nothing from the strong coupling approach that I didn't talk about selects out either of those possibilities.
Right. So in the schematic, I don't know if you haven't talked about the schematic yet. So when you go from spin anti-parallel to spin parallel, the valley wave function has to adapt.
The valley wave function won't do anything. So we're basically the order parameter for this guy is like you know, we have our valley X or valley Y, right? And then we have some spatial part, some orbital part, and then we have like what direction the spin in each valley is pointing. And you can change the direction in which the spin in each valley points however you want without touching the fact that the pair is symmetric or anti-symmetric under valley exchange. Does that make sense?
I think this is limited by my understanding. It's not.
Well, I mean, maybe equations would help here. I don't know. I'm not sure.
Yeah, let's. I'll ask for after.
Sure. Yeah, great. Okay. Yeah.
This is kind of a related question to the one about it. So sort of model does it rely on the fact the specific topological structure of the Trilayer Graphene block bands, or could you see a similar thing, say a twisted hexagonal semiconductor with block bands?
Like the way in which the flavor degrees of freedom are broken and like
yeah, like the like twisted HBN, twisted MLS2s have some signs of superconductivity at small. So,
right.
Is there any place where the graphene is actually playing a role, or is it really just once you have this microscopic?
Do you mean the extra dracone of the Trilayer thing, or do you mean just the? I don't think so. Well, I don't mean I only have thought about that graphene case, but the way in which I've thought about the graphene case has not been at that kind of microscopic level that you might want to think about. I don't know. Okay. Okay, so I'm just going to finish up soon. So I'm going to so what I've talked about so far is I'm basically claiming that there's the natural expectation from theory is to not have a singlet or a triplet superconductor in the system, and that explains this poly limit violation. Okay, that was one part of the data that I showed. The other part of the data that I showed was this plot, right? And okay, so let's just in 3 minutes, I'll just try to explain what my opinions are about this data. Okay, so I talked earlier about the fact that you have this TC being non-monotonic, but this like onset temperature where the pairs are starting to form being monotonic, right? So we want to understand this. So the most kind of when we saw this data, the first thing that we said was like, oh, it's definitely this. Okay, this we both really like this Lifshitz model thing. Anyway, so what's going on here is the following. So when you think about the Ginzburg-Landau theory for a superconductor, right? You have the phase of the order parameter, and the amplitude of the order parameter is frozen out when you're in the superconductor, and you just write down a theory for the phase degree of freedom. Okay, so you write down something like this. Now, normally people don't write this extra. There's this like extra higher derivative term for this scale. This phi is the phase of the order parameter, right? This is the Landau-Ginzburg thing. Normally people don't write this because it's like less relevant. It has more derivatives, right? But what we're claiming that is going on here is that this transition that's happening here is a transition where this K coefficient is changing sign. Okay, so I start down here, K is positive, and I just have some regular Landau-Ginzburg thing, which is not unusual. And then when I increase the field past here, K becomes negative, and then I add this. Then there's this term which is important for having the action be bounded, right? Okay, so this thing happens. Okay, why are we claiming that this makes sense with this picture? Okay, well, when K goes to 0 at this point, I'm claiming at this point, it turns out the critical temperature goes to 0. essentially because the critical temperature in this system is set by these vortices which are proliferating, right? It's KT physics. And if you don't have this kind of gradient term in the action, vortices are like very, very easy to create, sort of, right? Because, you know, you calculate the energy of a vortex by choosing some like vortex configuration for phi, and then you have like the logarithmically divergent thing, right? Blah, blah. The logarithmically divergent contribution to the vortex energy comes from this. But if I have these extra derivative terms, it actually means that the vortices are basically free. So if I don't have this term, the vortices just go everywhere and they destroy my phase coherence, okay? But that doesn't mean that they destroy the like tendency for the electrons to try to bind into Cooper pairs. The Cooper pairs are still there, but they just don't have phase coherence, okay? So that means that the Cooper pairs being there is why this is a smooth function of field. And the fact that they don't have phase coherence at this point is why this is a non-monotonic thing. So a consequence of this is, if this is correct, is that when this is negative up here, if you minimize this, the free energy for a theory kind of like of this form, you see that the minimum of the free energy is at finite momentum, right? Because this is like minus q squared, this is plus q to the fourth, so there's a minimum at non-zero q. So this would mean that this higher superconducting phase up there is actually like the pairing is occurring at finite momentum. This means that it's you can think of several kind of experimental tests to do this, but one thing that's kind of cool is that, you know, people talk about finite momentum pairing a lot in superconductors. It's very hard to, you know, to find, but the usual mechanism that's responsible for stuff like this is something called FFLO, and the physics of that is completely different from what we're talking about here. So it's kind of a new, if this is correct, it's kind of an interesting thing. Now, you know, for time, I'm not going to so this is like the phenomenological, hey, this kind of makes sense with the data, right? You would like to do better than that. And how you do better than that is not something that I'm going to explain, but it's not super hard to get a rough qualitative picture for convincing yourself that this kind of this k going to 0 is something that actually makes sense with the theory that you can do. I'm just going to skip that. Here's my summary slide. Okay, we have our superconductor. We have T-big, just drawing what I had. And this is what the spins do. And I have last slide. So yeah, experimental tests. So if this finite momentum thing I was talking about is correct, you can do some kind of like Josephson kind of experiments where these are like sensitive to the fact that part of the superconductor is at finite momentum pairing. I didn't talk at all about what we think is going on in this normal state. We have some thoughts about this being a topological insulator, and with there being edge modes and blah blah blah. That is something people can ask me about if they want. And then in the future, well, I don't know. I mean, you probably know better about the future than I do. But in the future, it would be cool. You know, we want to understand what's going on, what's the state that the superconductor is coming out of. You know, what the nature of that state is. We want to know what the you know form of the pairing symmetry is. Is it S wave? Is it P wave? We kind of have some data about that, but how that data informs the questions that we were thinking about in this talk is not totally clear. Anyway, so there's lots of interesting stuff, and I'll just end there. Yeah, thanks for listening.
Can see that data with that 8 Tesla in the right here. Okay, so let me just try to rephrase what you said.
Yeah, sure.
So at 0 field, at 1.3 Kelvin, so this is where the system.
Yeah, so this is like 5 Tesla.
1.2.
Yeah.
1.2 Kelvin. 1.3 Kelvin. So this is where the vortex anti-vortex pairs they bind. Right?
Yeah, yeah.
So then, okay, so that temperature scale is set by the basically superfluid density in the system.
Right.
Okay, so with the increasing field, you'll kill off this superfluid density. So the KT temperature goes down. Mm-hmm. Okay, so by 8 Tesla, you basically kill the the condensate. So
Right.
the condensate no longer has phase rigidity. So the
Right.
helicity modulus is 0.
Right. Right.
Okay, so let's buy that, and then let's say at a 0.3 Kelvin, I raise the field again to say to 10 Tesla. Somehow this phase rigidity reappeared.
Mm-hmm.
And but this condensate is different from the condensate at say 6 Tesla.
Yeah, it's kind of like the Cooper pairs are existing throughout. Yeah, I make the field bigger. The Cooper pairs are kind of like bound.
Yes.
And they're bound and they're bound and they're bound.
Yes.
And then they lose coherence, but they're still bound.
Okay.
And then more field and the coherence appears again, but they're still the same Cooper pairs. They're still bound in there. It's just their coherence disappears at this. The helicity modulus goes to 0. Well, it goes through 0. It becomes negative, but it does that without the Cooper pairs being unbound. Does that make sense?
I understand, but this is a very ad hoc.
Yeah.
Yeah,
I mean, I haven't like given you any. Just I think it's I haven't heard of a better way to explain this plot, but I haven't said anything quantitative at this point. So
predicts a non-zero in the second phase. That's what you're saying.
Yeah, I don't know. We were thinking of doing some Josephson things, but maybe there are better ideas. Of, the reason being that you can. I haven't talked about this displacement field, but I could imagine at least a setup where you have like you change the displacement field as a function of real space, and that means you have a high field regime, a superconductor right next to a low field superconductor. And then you can imagine doing some Josephson thing, and if there's finite momentum pairing, then you won't get that'll cause interference.
So it's from a different source, not all, but is it still like alcohol, or is it a specific method, or do you think it's more?
No, I think it would probably be continue. It would probably be a continuous function where the momentum gets larger as you go in this direction. Predicting exactly what it is too hard at the present time.
So these samples have lots of homogeneity. If you look at the IV curve, you can see 2 jumps.
Yeah, that's true. Yeah.
So what if I were to play devil's advocate?
Yeah, what's different regions or something?
The pair is around 90% sample. So it remains unchanged. And this phase and low temperature, this coherent phase that closes and reopens again. That's probably other 10%. If you decouple these, if you take away that Cooper pairing criterion, how would that impact the theory?
Sorry, so let me understand. So the let's see. So
because you're interpreting this phase space, and then you're saying that what happens here is that phase coherence go away, but the pair remains. So what if this behavior is only found part of sample, and from that part of sample, actually Cooper pair go away.
I see. Okay. So would the T onset be smooth there, or in that scenario?
In that scenario, the T onset also drops to 0.
Okay.
If you say that this discrepancy is due to sample homogeneity instead of some kind of intrinsic.
Yeah. But would I mean, to the extent that this is a smooth function, would it continue to be a smooth function if it was like coming from different regions?
Yeah, the
T onset
part of sample are just doing different things for some reason. Because I guess it's not so surprising, right? If the different part of sample are slightly different twist angles. The magnetic field scale for that to close that gap is, let's say, 12 Tesla.
Sure. Yeah.
If you go to 12 Tesla, you see kind of a similar behavior.
But why would you have like an increase in like all regions are being killed by the field, right?
Right. So that can I explain the shape? Because if you sit at a 0.3 Kelvin, you just sweep the field up. The resistance going up, going up, and then going down again. And I assume get it to like a 13 Tesla, will go back up again, right? So at some point, let's say you go to 20 Tesla, you'll kill superconductor, all the pairs. You got to, right?
I think I see what you're saying actually.
So the resistance, so fix the temperature, increase in field, the resistance going up, going up, to 8 Tesla start going down, right? And then they get 10 Teslas is the minimum, and then when you get to 15 Tesla, go back up again. Something like this happened in low temperature superconductors. Now we yes, it's called a peak effect. And then Larkin, the same guy, the same L explained it.
Slightly different.
Yeah, I think
I know it's definitely is very different.
yeah, this also happens in some like uranium superconductors. They have a re-entrant field kind of thing, but that physics is also very
That's
different.
FFL.
Yeah.
That's heavy fermion. That's understood.
Right. But here, you know, we're not.
If that's due to vortex phase trend.
Yeah, it's different. Yeah.
This is definitely different.
Right. And it's not FFLO because we're not. You know, we're not like. If you have formed singlets, then you have to pay some cost to gain the magnetization energy, but we don't have to pay that cost. So it's the physics of FLO.
It's either a giant experimental artifact.
Yeah.
That goes away with next graduate student.
Right.
Postdoc. And then we stop talking about it. Or
I guess we'll see.
Come back with a better explanation.
Yeah.
At this point, I'm not convinced.
I've only been talking about one experiment, right? So
no.
That's
you're arguing
really.
that somehow the same Cooper pair loses phase coherence in the magnetic field, and then when I give them more hardship, somehow they get together and become a superconductor. But that's just it doesn't make sense to me.
Yeah. So I mean, you can try to the way in which we backed this up was to, you know, I didn't really come back to this, but we had the bilayer graphene, then we had this like Dirac fermion cone, and the Dirac cone was like being hybridized with the other fermions as you turned on the field, right? So you can try to compute what the effect of that hybridization is, right? And you can like integrate out this Dirac cone and try to see what it does to the superconductor. And if you calculate that, you see that it reduces the phase stiffness and stuff. And so you can imagine that the effect of adding into this Dirac fermion is like qualitatively produces this thing, but
the two competing effects, right? So what the saying is here with increasing field, the TC gone up, right? So there's something that effect is being suppressed by magnetic field, right?
Yeah. Right. Yeah. Exactly. Yeah. And so, to the extent that you can try to compute that, it kind of agrees with this.
Any other questions? Any Zoom questions?
I don't think so.
Okay. No other questions.
Okay.
Thank you.
Thanks, guys.